This is our second video on Chapter 2, Aqueous Chemistry. We'll be looking at water and some of its interesting properties, but more particularly at hydrogen bonding. As far as our biological molecules, we're more carbon than anything else, but by mass we're mostly water, about 60%. So let's look at some of the bonding interactions in water. First of all, the molecule itself is composed of an oxygen atom covalently bonded to two hydrogen atoms. Recall from our last video, this means they're sharing electrons. Now, even though there are only two covalent bonds, the structure of water is actually tetrahedral, and that has to do with the fact that the oxygen atom also carries two sets of unpaired electrons. It's not a perfect tetrahedron, though, because they are unshared. It is the presence of these unpaired electrons that makes water a polar molecule. Recall what we mean by polar. It means that the atoms have dipoles, that is, partial charges, indicated by a lowercase delta symbol. In the figure on the upper right is our water molecule. Because of those unpaired electrons, the oxygen carries a partial negative dipole. In the covalent bonds between oxygen and hydrogen, there's an unequal sharing of the electrons. Oxygen is more electronegative, and so it holds on to more of those electrons, so there's a partial positive charge on the hydrogen atoms. We can align these dipoles to form a hydrogen bond, just like we can align the opposite ends of magnets together. In this case, there's some covalency, that is, some sharing involved. In the figure on the bottom of the screen, you'll see a ball and stick model of two water molecules. The oxygens are pictured by the red spheres and the hydrogens by the white spheres. Notice the partial negative charge on the oxygen and the partial positive on the hydrogen. So these two can come together to form that hydrogen bond. In this illustration, the sticks represent the covalent bonds, and the dashed, highlighted in yellow line is the hydrogen bond. Now, although in the next video we're going to talk about the strength of these hydrogen bonds, it is an average. You could have a stronger or a weaker hydrogen bond. Recall that in order to form any kind of a bond, the atoms have to come close enough together, and so there are both proximity and orientation features. In the case of the figure on the left here, we have a linear alignment of the atoms involved in the hydrogen bond. Oxygen, hydrogen, oxygen in a linear arrangement. This allows for maximum overlap of those orbitals, and remember that means the shortest distance and the strongest bond. In the figure on the right, however, the alignment is not strictly linear, and so in that case the overlap is slightly less, and so it represents a weaker hydrogen bond. One of the interesting properties of water has to do with its ability to form these hydrogen bonding interactions. It means it's highly cohesive. In the illustration here, one water molecule can hydrogen bond with four others. This depends to some degree on temperature. Recall that we have two partial negative dipoles because of those unshared electrons, and two partial positives on those hydrogen atoms, and so each one of those can form a hydrogen bond. Now, the lifetime of these hydrogen bonds is very short, on the order of picoseconds. One of the ongoing themes that we'll see in biochemistry is that the interaction between molecules is often very dynamic. So in this case, a water molecule is in nearly constant motion. Now, of course, water is a liquid at room temperature, and because of this highly cohesive nature of the water molecules, it creates a high surface tension. Let's look at the figure at the bottom of the screen here. If we look at each one of those spheres as representing a water molecule, the one in the center of the screen here is a water molecule that is surrounded 360 degrees by other water molecules, and so there's a maximum degree of hydrogen bonding interactions. However, if you look at the surface molecules, they can form hydrogen bonds with one another or with water molecules below them, but there are no molecules above them to form hydrogen bonds. In order to equalize the strength of the interactions with those within the body of the water, those molecules on the surface have a stronger interaction with one another, and that creates a high level of surface tension. So what this means in the case of our strider here, water strider at the top of the screen, it means that he can float on the surface of the water, and that's because the weight of his body is less than the strength of the interactions of those surface water molecules. Now, because of the hydrogen bonding interactions of water, it also means that water in the solid is less dense than the liquids. Recall that when we form those hydrogen bonds, we want that linear arrangement, and so there's a geometric constraint on how many that we can form and the order in which they form. So in the solid, we have this very cage-like structure, a very porous molecule. And so what that means is as it solidifies, water expands. And so it becomes very porous, and therefore ice floats in our refreshing beverages, and it also means the little fishies don't freeze in the lakes. Let's look a little bit more at these hydrogen bonds. In water, we have both covalent and hydrogen bonds. Now recall, when we talk about the covalent bonds, we mean the bonds within the molecule, the intramolecular interactions. When we're looking at hydrogen bonds, we're looking at an interaction between two molecules, at an intermolecular interaction. So in the figure in the center of the screen here, we're looking at two water molecules. The solid lines are the covalent bonds within the molecule, and the hydrogen bond is the dashed line, indicated by the blue bracket here, and that's the interaction between two separate water molecules. Interestingly, only a hydrogen atom will work. It's the only atom whose nucleus can get close enough to that lone pair to do that degree of sharing. No other element will work. Recall also that the covalent bond in water, that is within the molecule, is shorter and stronger than the hydrogen bond between water molecules. Water can also hydrogen bond with other molecules besides itself. All you need is an electronegative atom. Often it's nitrogen, oxygen, or sulfur in biological systems. So in the figure on the bottom of the screen here, we have water hydrogen bonding with an alcohol. On the right, we have water hydrogen bonding with an amine. In each case, the covalent bond is the solid line, the hydrogen bond is the dashed line highlighted in yellow. So in each case, we have a hydrogen atom between two electronegative elements. In the figure on the left, it's hydrogen between two oxygens. On the right, hydrogen between oxygen and nitrogen. You want to become familiar with how to recognize hydrogen bond donors and acceptors, so let's briefly review that. The blue arrows indicate hydrogen bond acceptors. That is an electronegative element, one towards the right of our periodic table with lone pairs of electrons to share. In this case, they're both oxygen, an oxygen and a carbonyl group. A hydrogen bond donor would be an electronegative element that has a hydrogen atom to share, and so that's indicated by the green arrows here. Water on the left is our donor, and we have an amine group within a peptide bond as our donor on the right. In our next lesson, we want to look at what other kinds of bonds we see in biological systems and how do they compare with covalent and hydrogen bonds. And we want to see another of water's interesting properties, that is, how and why is it the universal solvent.